Hey everybody, Daniel here from Basement Tech. Well, regular subscribers and or watchers to the Basement Tech channel undoubtedly remember that I'm in the process of converting this CNC Shark machine from its proprietary controller to one based on LinuxCNC. You may also recall that I said in the last video, I'm going to leave this machine a little bit more open for research and experimentation. And to that end, I mounted up the Gecko G540 on this piece of wood together with a little bit of a power distribution terminal strip. I've also identified the 48 volt power supply out of my junk box that I'm ultimately going to use in this machine. But let's get to limit switches. There are a couple different kinds of limit switches that we're going to represent in this system right away. One is the typical clicky type micro switch, which we'll talk a lot about in this episode. And the second is this, which is an inductive proximity limit switch. Using no moving parts, when metal gets close to it, it generates a signal much like the press on the clicky switch. We may or may not get to talk about this one fully in this episode, but rest assured we'll do so in the next one, if not. So let's go around the corner and talk about this type of limit switch, the clicky limit switch. Every limit switch implementation requires a few different components. The first is what's typically called the trip dog. In the last episode, I piqued your curiosity by showing this piece of aluminum. I'm going to mount that up onto the machine and you'll get an idea right away of what that's going to do. The second component, of course, is the switch itself. In this case, the clicky micro switch. And the third thing is some kind of an input into the system so the system can react when the limit switch is tripped. In our case, the Gecko G540 provides such an input. Well, I repurposed a couple of existing mounting holes on the Z-axis carriage and a couple of somewhat longer screws to mount this plate such that it moves back and forth with the X-axis. You can imagine then, if I were to place one of these little micro switches, say in this kind of a position, as that X-axis moves, in this case to the right, it's going to push down and trip the switch. So what it's going to take then is drilling and tapping a couple of threaded holes to mount this switch in the desired location. Now, I was a little nervous, not about the repeatability of the micro switch. These switches are highly repeatable in terms of where they trip. But I was worried about my ability to drill the holes precisely, and I wanted a little bit of adjustability. So I milled up a couple of mounting plates that are going to serve two purposes. Number one, yes, it's going to give me a little bit of adjustment in case my holes are not drilled exactly where they belong. But secondly, if I were to use a different switch down the line, in the future, I don't have to keep drilling and tapping holes in the machine itself. I can either make a new plate or drill and tap a second set of holes. So now this then is going to mount on a couple of holes. It gives me a little bit left and right motion and a little bit of angular adjustment that's going to allow me to optimize the position of the switch relative to where I want it to trip. Okay, well there you have it. This one mounted, as I showed in all the little clips, and rinse and repeat on the other side. Let's get on to wiring these things up and making them do something useful. The G540 senses a change in its input when one of its pins, in this case pin 1, over here on the left, is either pulled to ground or released from ground. Microswitches in general, like the ones we're using, have 3 terminals, a so-called common terminal, a normally closed, and a normally open. We're going to make use of the normally closed terminal, and that's the terminal that's connected to the common terminal when the switch is said to be at rest and not pressed. Think of the signal as coming from originating at this ground, looping through both switches, the normally closed at rest, and back to the G540's pin 1. And that pulls it to ground in the normal resting state. This implementation may seem a little bit backward, but this is seen as a little bit more reliable when it comes to limit switches. When we press one of the switches, this loop is broken and pin 1 goes from being grounded to being high. In this case, it's about 11 volts, a voltage that the G540 can sense, and it knows something bad has happened, or not necessarily bad, but something has happened with the x-axis. Well, off the paper and back to the metal. Here's the black wire I was talking about here that connects to the negative terminal of our power supply. It loops through this gray cable all the way over here to the normally closed terminal on our X-Max switch. It loops through there, back on this red wire. The red wire loops through this switch and returns to the G540 through that red wire. So you can imagine when both of these switches are closed, if you will, in the normally closed resting position, this red wire is at the same potential as the black wire, which is ground. When one of the switches is pressed, breaking the circuit, the G540 pulls its own input up to positive and senses that as an active signal indicating that something has happened. Okay, with the wiring done, it's time now to tell LinuxCNC where to find this new and useful signal. I don't want to go into a very extensive how-to at this point. I'll do that in a separate video, but I did want to just give you a little taste of how far LinuxCNC's come when it comes to configuration. So there is a new wizard, if you will, that's used for doing configuration. So this is it. I'm going to say modify my existing configuration. That is the name of it. Again, I'm not going to go through everything. I'm going to jump kind of forward to the place where I know it starts to talk about signals, and that's here. Okay, so when I get to this page that's talking about signals, I have identified that this one here is the one I need. And again, I'll go over these details in an upcoming video. But when I go down here, I go to Limits, Home, Shared, and it's presenting me with all of these very useful and appropriate options. So I come down here to X, both limits, that's top and bottom, and I'll explain why that makes sense, and Home. Remember, the limit switches are in series, so they share one input. So that says this one input is both top and bottom, and the system figures out which direction you're moving based on context, which direction is the axis moving. And same with homing. So I just say, choose that one. Now, again, I'm going to just jump forward and save this change. Almost done, and I say done. And it says it has been built and saved, and I say yes. And that's all there is to it to do a simple configuration change. Well, let's see these switches in action. You might remember when I configured this pin, I said it was both for limits and homing. Well, let's see the homing sequence, since that makes use of the X-Min switch. I hope you found this video useful and maybe a little bit educational, maybe even a little bit inspiring if you're a CNC Shark owner and thinking about moving to a more open architecture. Coming up in other videos, I will do one on configuring LinuxCNC for this particular set of hardware. Also, I realized I probably should talk about some of the design criteria when it comes to voltages and currents in this machine. I'll make that a separate video as well. But the very next video will be implementation of those inductive limit switches on the y-axis. That's going to be very cool. I hope you tune in to see that one. If you like this kind of video, please give it a thumbs up. If you really like it, subscribe and hit the button that says, let me know when Dan's talking about CNC Shark conversion to LinuxCNC again. Thanks, bye.